Good morning, this is Dr. Jingbo Louise Liu again. Today we are going to continue and then finish the chapter 10, the molecule shapes. We are going to be focusing on two different topics, the valence shell, electron pair repulsion, which is also called Vesper theory. Followed by, we are going to give you the one-on-one example of the molecular shapes. The last topic will be the molecular polarity. We show you very briefly about how you are going to determine the molecule polarity. In terms of the valence shell, electron pair repulsion theory, we need to know three key points. Point 1. Each group of valence electrons around a central atom is located as far away from each other as possible. This has a goal to minimize the repulsions between the different electrons. Point 2. A group of electrons is any number of the electrons that occupy the localized region around your atom. The group of electrons can be a single bond correlating to 2 electrons, can be double bond related to 4 electrons, triple bond, 3 electrons, can be a lone pair, can be just a single electrons. All of this are counting as the single electron group. The third point, the electron group repulsion and molecular shapes are very critical. Electron group repulsion related to the different electrons. Your molecular shapes is more involved in the location of the nucleus. We are going to learn 3 metric structures. The first one, the linear structure. Second one, the trigonal planar structure. Third one, tetrahedron structure. Fourth one, trigonal bipyramidal structure. The last one, called octahedral structure. Based on these 5 different structures, we can derive other types of structures. Let me emphasize the difference between the electron group arrangement and your molecular shape. To restate, the electron group arrangement is defined by both bonding and non-bonding electron groups. The bonding can be single, double, and triple bonds. The non-bonding can be the lone pair, 2 electrons, can be a single electron. The molecular shape is the 3-dimensional arrangement of the nuclei joined by the bonding groups. This is defined only by the relative positions of the nucleus. You are not going to consider the electrons, but only consider the position of the nucleus. Your molecular shape is classified using the designation showed below. A, X, M, E, N. This capital A represents central atom. This whole designation is called Vesper formula. You have your molecular formula. You learned another one called Vesper formula. In your Vesper formula, you put your central element in the front, followed by X surrounding element, and you also identify the number of lone pairs or the number of non-bonding valence electrons, usually represent lone pairs. As we mentioned, this capital X represents the surrounding atoms. Capital E is the non-bonding valence electron groups. Generally speaking, most of the cases represent the lone pairs, 2 electrons. The smaller m and the smaller n are the positive integers. The number m is the number of your surrounding atoms. How many surrounding atoms are in your VSEPR formula? Smaller n usually represent the number of your non-bonding valence electrons. As I mentioned, normally refers to the lone pairs. In most of the cases, lone pairs can be single electrons as well. We also need to know the band angle. Band angle is the angle formed by the nuclei of 2 surrounding atoms with the nucleus of the central atom. Let's see, your A. Your A is your central atom. Your central atom nuclei and the 2 surrounding atoms, X1 and X2. This angle you call the band angle. The band angle shown in this figure 10.2 are the ideal band angles. They are ideal. They are determined by the basic geometry alone. The real band angles can be deviated from the ideal angles. For example, if you have AX3, these 3 elements surrounding atoms are identical. In this case, this band angle and the real angle are going to be the same, will be 120 degrees. If you have central element A, 2 surrounding atoms form the single bond. You have the 3rd surrounding atom forms double bond with A. A and Y forms double bond. In this case, the real angle will not be the same as your ideal angle. Real angle and band angle of ideal band angle will be different. If you have A surrounded by 2 X's and 1 Z, because X and Z, they are different, therefore, the band angle, ideal-wisely speaking, will be different from the real band angle. Imagine this A bonded with 2 elements and 1 lone pair. Your real angle also different from the band angle. So the ideal band angle determined based on the basic geometry alone. The real angles deviate from the ideal values in many cases. Let me show you the first group of the structures. So if you have A, which bonded with 2 different atoms, AX2. In this case, these 2 X's and A, central atom, they form single bond. This group, electron group, located opposite to each other to minimize the, repulsion. In this case, you form a band angle 180 degrees. The band angle is 180 degrees. This structure, you call it linear structure. Linear structure, you form a single straight line. The examples: CS2, CO2, BeF2, or HCN. You have different ones. So in this case, you also can have this part, this X, either of this can be a lone pair. You have your A represent X. You have 2 X's. A represented, by the red sphere. The X's represented by these dark gray spheres. And you have another case. You have 1 X. The second X represents the electron lone pair. In this case, you don't really have band angle. You only have 2 atoms. Let's continue. Sorry for this interruption. So if you have AX3, you are going to have a structure called a trigonal planar, such as SO3, BF3, nitrate, NO3 negative carbonate, CO3 2 negative. If one of these X is replaced by a lone pair, such as SO2, sulfur dioxide, O3, ozone, PbCl2, SnBr2. In this case, you are going to form a molecular structure which is called band or V-shaped structure. V-shaped or band structure. So this lone pair, this electron arrangement is not going to be taken into consideration to determine your molecular shape. Molecular shape only consider this nuclei, central nuclei, and 2 surrounding nuclei. The third structure will be the tetrahedral structure. Before we go into the tetrahedral structures, let me emphasize the factors affecting the bond angles. First one is called non-bonding pairs, also called lone pairs. If you have this lone pair, the lone pair repels bonding pairs more strongly than the bonding pairs repel each other. If you have SnCl, there's a bonding pair, SnCl bonding pair. These two, the repulsion is less. This lone pair repel the chlorine more than the Sn chlorine. So therefore, the angle between the SnCl will be decreasing. Your band angle will be decreasing. The second factor, double bonds. Imagine you have we call the formaldehyde, H2CO. The ideal band angle will be 120. However, you form a double bond. The double bond has greater electron density. You have 4 electrons. Single bond 2 electrons. Double bond has a greater electron density than a single bond. Therefore, the double bond repels the single bond electrons more than the single bond repels single bond. In other words, carbon-hydrogen single bond, that bond angle will be decreased from 120. What we found is 116 degrees. As we mentioned, the third molecular shape is originated from tetrahedron electron group arrangement. If you have the electron group arrangement, which is a tetrahedral, you have a central atom, you have element 1, surrounding element 2, surrounding element 3. These 3 atoms, they are located in the same plane. Your central element lifted up, the very last pointed up. The band angle for this structure is 109.5. Based on this electron group arrangement, you can have totally 3 structures. One for the molecular structure is tetrahedral. Second one is called trigonal pyramidal. If you have one surrounding atom replaced by the electron pair. If you have your surrounding atoms replaced by 2 pairs, 2x replaced by 2 electron pairs, you are going to also to have the band or V-shaped or angular. You form the angle, band, V-shaped or angular structures. The examples are methane, silicon tetrachloride, or sulfate and perchlorate. You form a very ideal 109.5 degree. Imagine one of these electron pair, this electron or paired electrons replaced by a lone pair. We learned this lone pair repels the single bonded electron more than they repel from each other. Such as if you have NH3, PF3, chlorate, hydronium. So this band angle, the band angle between central element with 2 surrounding atoms, this angle will be smaller than 109.5. The third molecular structure based on this tetrahedral electron group arrangement can be band, or V-shape, or angular shape. If you have two surrounding atoms replaced by two lone pairs, such as in water, H2O, such as in silicon dichloride, so two lone pairs, this water OH bond will be much smaller than 109.5 because lone pairs repel each other stronger, repel the single bonded bonds also stronger. So make this bonded angle, the band angle, much smaller. The fourth molecular shapes of the trigonal bipyramidal electron group can be differentiated into 4 different types. If you have all these surrounding atoms of F's, X, F5, PF5, arsenate, trifluoride, if you have these structures, so your molecular shape will be essentially the same as your, shape for the electron group arrangement. You have two angles. So this angle, this 90-degree angle, this is a trigonal planar and perpendicular to these two bonds. In this case, this angle is a 90 degree. And in your trigonal planar, this trigonal planar, 120 degree. If you have one of these surrounding atoms is replaced by one lone pair, by one lone pair, you are going to obtain a seesaw structure. Remember this one. This is going to be on the side of your trigonal planar. The examples are sulfur tetrafluoride, so XeO2F2, etc., etc. The band angle also, in this case, you do have the angle may be smaller than 90. This angle will be smaller than 120. It depends. The third molecular structure shape, if you have two axes replaced by two lone pairs, what you are going to receive, you essentially receive a T-shaped, but this angle actually is smaller than 90 degrees. If you have three lone pairs, those three lone pairs will make your structure to form a straight line, a linear structure. The examples are listed as ClF3, XeF2, etc., etc. These are the fourth molecular shape. The very last one will be tetrahedral. In terms of these different structures, particularly when we have this trigonal bipyramidal structure, what you found? You found two different positions. One is called equatorial, another one called axial. You have two different positions in terms of your electron group or in terms of your surrounding atom. In the 5-electron group system, you are going to find two different positions for the electron groups. And you also found two ideal band angles. The first position you call the axial position. The second position called the equatorial position. These equatorial positions, they are located in the equators. The axials is perpendicular, essentially perpendicular to your equators. The one in the axial, that band, is perpendicular to the equator, meaning you have 90 degree. The band angles for the equatorial and the equatorial, they are going to be 100 degree. Where possible, the lone pairs in the 5-electron group system occupy equatorial position first, such as you have AX4E. So your equatorial position will be occupied first. You form a seesaw structure because this repulsion is bigger, so you need a higher space. Then for your tetrahedral electron group arrangement, so you are going to have 3 different structures, molecular shapes: octahedral, square, pyramidal, square, planar. If your electron group arrangement is tetrahedral, you have 1 band angle, 90 degrees. Because the one you have 4 atoms, 4 surrounding atoms are located in the same plane and they are perpendicular to each other. You have 90 degrees. And then the atom above the plane, atom below the plane, also perpendicular, such as SF6. You have a 90 degree for this special case. If you have I, in terms of the I, you have oxygen at 5 different fluorines, your band angle will be for this, if this is your oxygen, this angle will be slightly different by 90, but could be negligible. If you have 1 electron pair, such as 1 lone pair, replace one of the X, becomes AX5E. In this case, you are going to form a square pyramidal. So these 4 surrounding atoms form a squared planar structure, 1 atom above. So your lone pair is going to be located in the bottom of your structure. The very last one, if you have your 2x elements, atoms, replaced by 2 electron lone pairs, those 2 electron lone pairs will be opposite to each other, such as XeF4, you are going to form a square planar structure. There's the different 5 matrix structures based on the electron group arrangement, and then your molecular structures can be derived from these 5 different structures. Your molecular shape and molecular polarity are closely related to each other. Overall, molecular polarity depends on both the shape and your bond polarity. The polarity of a molecule is measured by its dipole moment mu. This dipole moment has a unit by d. Dipole moment mu is the measurement for the polarity of your molecules. A molecule is polar if this molecule contains 1 or more polar bonds. The individual bond dipole do not cancel. If you have linear structure such as carbon dioxide, carbon oxygen, carbon oxygen, they are polar bonds, but 2 carbon oxygen bonds, that dipole cancel each other. So make sure in your molecule you have polar bond or polar bonds, and each bond cannot cancel each other to cancel these dipole moments. So that's 2 key points. For example, if I have HF, my hydrogen fluorine is a polar molecule. Your hydrogen is more positively partially charged. Your fluorine, which is more electronegative, will be negatively partially charged. If you apply the electrical field, your electrical field, if it's off, these molecules stay randomly distributed. If you apply the electrical field on, imagine I have a positive, I have negative. What's going to happen? The more positive end will be aligned towards your negative terminal electrical field. On the other hand, the positive electrical field will be more aligned for your negatively partially charged. Your fluorine end will be facing to the positive end of the electrical field. In other words, your electrical field is off, molecules are randomly oriented. Your molecules become oriented when the electrical field is turned on. The molecules negatively partially charged end will be facing towards, aligned towards the positive electrical field end. And then bond polarity, bond angle, and bond moment. For example, you have CO2. A couple minutes ago, I mentioned carbon dioxide is a non-polar molecule. Carbon and oxygen bond is a polar bond. The reason is the electronegativity of carbon is 0.25, oxygen 2.5, oxygen 3.5. Therefore, carbon-oxygen bond is a polar bond. Electronegativity difference resulted in the bond polarity. However, these two polar bonds, they are cancelled each other. One pointed from carbon to oxygen, from left to the right, another one pointed from carbon to oxygen. So these two bonds cancelled out. Your carbon dioxide is a linear molecule. The bond angle is 180, and the individual bond polarity, therefore, cancelled. The molecule has no net dipole moment. The dipole moment mu is 0 dBi. The second molecule, your water, H2O. Hydrogen and oxygen, they have different electronegativity. Therefore, your hydrogen and oxygen the bond is polar bond. Hydrogen-oxygen bond are polar. Couple minutes ago, we mentioned in your oxygen you have two lone pairs. Therefore, your water molecule forms a band structure. Water molecule, either you can say it a band or V-shaped, letter V, V-shaped geometry. So the individual band polarity cannot be cancelled out. So pointed from your hydrogen to the oxygen, so make sure in your hydrogen end you put a little positive, pointed from positive to negative. These two individual bond polarities do not cancel. Therefore, the molecule has an overall molecular polarity. The oxygen is electronegative. The polarity will be more negatively partially charged. Remember, this is called partially negatively charged, while your hydrogen ends will be partially positive. Your negative part will be related to the higher electronegativity. I think the last point, so is related to the bond polarity, bond angle, and bond moment. So if you have CCl4, this carbon-chlorine also have different electronegativities, meaning carbon-chlorine bond is a polar bond. However, all of these four different polar bonds, they cancel each other. So this molecule methane is a nonpolar molecule. If you replace one of the, this is not methane. Methane is also a polar molecule. This is called tetrachloromethane. This CCl4 is also a polar molecule. If you replace the Cl by the hydrogen, one of the Cl replaced by hydrogen, so carbon, hydrogen, carbon, chlorine, carbon, chlorine, they're all polar bonds. However, these are carbon-hydrogen bonds, so they are different polar. The bond polarity, generally speaking, will not be cancelled out. Therefore, the molecule is a polar molecule. The measurement for the dipole moment mu equals 1.01 dBi.